Okay, show of hands. How many of you have felt that surge of satisfaction after finally getting out of a maze? Maybe you were forced to go to a corn maze for a middle school field trip. Maybe you were an ancient Greek prince who wanted to stop a half-bull man from eating a bunch of your fellow Athenians. Or maybe you were a mouse in some scientist's lab who knew a snack was at the end. Whatever your personal experience, it probably felt like you had to put some kind of smarts into it. But the thing is, you don't need to have any smarts at all to solve a maze. You don't even need to have a brain. Heck, you don't even need to be alive. So let's take a look at 5 brainless things that can solve a maze and how they manage to do it. The humble slime mold is probably the most famous example on our list, so let's tackle that one first. If you've not heard of this kind of life form before, they're, well, super weird. For one thing, slime molds aren't actually mold or any kind of fungus. They're a unique kind of single-celled organism that just look like mold because some of them can dissolve the membrane separating their individual cells, merging their innards together. The structure this forms, called plasmodium, is basically a single cell that's big enough to see with the naked eye. And a plasmodium can be shaped into filaments and tubes called pseudopodia, which can stretch and reach out to nearby food sources. Back in 2000, some researchers in Japan and Hungary filled a little maze with a plasmodium of the species Physarum polycephalum and put food sources at 2 different ends of the maze. Within a few hours, almost all the plasmodium that wasn't on the shortest path between the 2 food sources had faded away. The slime mold was essentially conserving resources. It chose to only maintain paths through the maze that were most efficient at transporting nutrients. But how did it know which path was the most efficient to keep using? Well, it's tricky to say for sure. We know it's using some form of chemotaxis, which is when a living thing detects and follows signals coming from a chemical somewhere. But the full details of how that slime mold optimized its path were unclear. So in 2010, some researchers in Japan and the UK created a mathematical model based on that same slime mold species to gain more insight. The model focused on a feedback loop between the thickness of the plasmodium tubes and the flow rate of stuff through those tubes. If the flow rate got too low in a given tube, meaning there weren't enough nutrients passing through it, the tube would disappear. That left the tubes transporting the most nutrients and also the most optimum path to transport those nutrients through the maze. But you may already be familiar with this research paper because of what else the team did. They also used a slime mold to recreate part of the Japanese transport network. In this experiment, they placed food sources on a mini-map of Tokyo and some surrounding cities, with each source representing the various population centers. The slime mold was then left to form plasmodium tubes between all of them. Sure enough, just by optimizing its own food transport, the slime mold managed to create a series of tubes that was organized as efficiently as the real one. If you're feeling envious of a mindless blob of critter, you can find comfort in our next example. Researchers have also coaxed human cells into solving mazes. The principle is similar to before, using chemotaxis to move as efficiently as possible toward a chemical source. And if you think about it, it makes sense that certain cells are good maze solvers. Bodies are complex, and not all cells just sit in one spot for the whole of their lives. Think white blood cells having to go somewhere specific to fight off an infection, or a cancer that starts in one organ spreading to a completely different one. So cells like these have some clever tricks up their sleeve to help them navigate their surroundings. For example, they can produce their own chemical signals for other cells to follow them. By working together like this, these cells don't have to rely solely on a signal coming from the end of the maze, and they can also navigate even more complex paths. In fact, in 2014, one group of researchers created a competition to push cell navigation to its limits. This was the Dicty World Races, named after one of the cells contestants could use, an amoeba called Dictyostelium, which biologists often use as a model organism in their research. You'll note that that's not a human cell, but other contestants chose to race a human blood cancer cell instead. The actual maze was set up to imitate the cell's natural habitats, and 14 teams each brought their genetically engineered cells to clear it as quickly as possible. A group from the Netherlands were declared the winners after their Dicty cells took 48 of the top 100 race times. It's a charming story from the world of science, but this wasn't just fun and games. As I mentioned before, some teams were working with cancer cells, and understanding how they move through tissue is critical if scientists want to develop treatments to stop cancers from spreading. So far, everything I mentioned has at least been alive, with mechanisms to sense their surroundings and react to them. But can anything non-living solve mazes? Well, sure. If you release a gas into a maze, by simple diffusion and random chance, some of the particles will eventually reach the exit as the gas explores every single path. That is boring, though. So instead, say hello to the maze-solving liquid that can traverse a maze without going down any wrong paths. In 2018, a research team filled a small maze with milk, then put a blob of food dye at the entrance. When they added a drop of liquid soap to the blob of food dye, that blob suddenly spread through the maze, but only down the path that led to the exit. This apparent magic trick relies on a phenomenon from fluid mechanics called the Marangoni effect, which is a consequence of a much more well-known phenomenon called surface tension. When you've got some amount of liquid, all the molecules in that liquid are pulling on each other a little bit. For most of the molecules, they're completely surrounded by other molecules. So the pulling comes from all directions equally and basically cancels out. But at the surface, that pulling is lopsided. So the molecules are constantly feeling a slight tension, hence surface tension. As for how this maze experiment worked, it's because soap is a surfactant. That means it lowers the nearby surface tension when it's added to another liquid. Milk also naturally has trace amounts of its own surfactants, but no, that does not mean you dairy lovers are constantly drinking soap. Imagine you're a blob of food dye floating in a milk maze and some soap gets plopped next to you. Suddenly, you have a neighbor that isn't pulling on you quite as hard as you were used to. So you start moving in the opposite direction, toward the milk that's pulling on you more strongly by comparison. But what happens whenever you reach an intersection in the maze? Well, you'll be drawn toward the path with more surface area ahead. That's because the scientists designed your maze so the exit features a large reservoir of milk. In other words, the correct path to take, compared with all the dead ends, has a much bigger surface area. And since the amount of surfactants in milk is low compared with the soap, a path with way more surface area creates a much lower surfactant density. And remember, you, as a blob of dye, are being pulled away from the surfactants. So you get pulled toward the exit. No thoughts needed on your part. Just the laws of physics. We've got 2 maze solvers to go, but just like all this science, we need funding. So here's an ad. This SciShow video is supported by Brilliant, the online learning platform designed to help you reach serious learning goals. Instead of passively watching lectures, this year you can be more active about learning with Brilliant's interactive problems and challenges. Through active problem solving, you can build genuine understanding and tick off that New Year's resolution to deeply comprehend a new field. And you'll have plenty of fields to choose from, because last year, Brilliant doubled their content library to include timeless topics in math and science, and cutting-edge concepts in AI, quantum, and beyond. To learn for free on Brilliant, go to brilliant.org/scishow, scan the QR code on screen, or click on the link in the description. They're also giving you unlimited daily access to everything on Brilliant with 20% off an annual premium subscription. Our non-living maze solvers only get weirder from here. Next up is the stuff electricity and fire is made of: plasma. In 2002, a UK-US team etched a thumbnail-scale maze into a glass chip, filled it with low-pressure helium gas, and ran an electric current through the whole thing. The aim was to observe a well-known effect called a glow discharge, where the current turns a gas into a plasma. The resulting plasma is full of charged particles called ions that are excited, energetically speaking, and want to emit some of that energy to stop being so excited. When they do, they let off a distinctive glow. If you're wondering, is this how some neon lights work? That answer is yes. But here's the thing. You may remember from school that an electric current will always try to follow the path of least resistance, which almost always means the shortest distance. So if you put your 2 electrodes at the entrance and exit of a maze, the current will only form glowing plasma along the shortest path through that maze. Like with the food dye, the laws of physics force it down one path. But unsurprisingly, the specific laws of physics that apply here are different. When you switch on the current in a circuit, an electric field spreads over it at the speed of light. any charged particles in the circuit will react to this new field and move around. But since they're charged particles, they're also emitting their own tiny fields, so their movement winds up changing the larger field too. And on paths with more resistance, the charges rearrange themselves to cancel out the flow of current. This feedback loop happens at near light speed, so the current is able to explore every path in the maze almost instantly when it's switched on. And this exploration and rearranging of charges always leaves only one path for the current to follow, the path of least resistance. Of course, the scientists behind this plasma maze didn't stop with a mere explanation of the science and a simple maze design. To one-up themselves, the team etched a road map of London onto glass. By putting electrodes at different points on the map, they could make the plasma show the shortest route between any two locations. So if you want to know the fastest route from Victoria Station to Imperial College London, and your friendly neighborhood slime mold is on vacation, just ask your friendly neighborhood glow discharge plasma instead. And finally, let's talk about how one group of Italian researchers got a beam of light to solve a maze. Here, the centimeter scale maze was made out of a special optical material with branching pathways etched into it for light to follow. The light could then bounce between different pathways in ways that looked a lot like choosing paths to take in a maze. But because the light is doing all that bouncing, it winds up traveling slower than your standard speed of light speed you wind up memorizing if you go to college for astrophysics or whatever. That meant the team could test to see how fast the light could find its way out of the maze under different circumstances. Because just like letting a bunch of gas into a maze, light would eventually make it to the end simply by bouncing around randomly between the different paths. But could the light be coaxed into traversing the maze more efficiently? It turned out, yes. By exploiting special quantum properties of the light, like its ability to take multiple paths at the same time, the researchers could shorten the time it took their light to reach the exit. But interestingly, they found that they could improve the light's maze-solving abilities thousands of times over if they also introduced just a little bit of noise to the circuit. In other words, effects that destroy the quantumness of the light. To be more specific, they made sure their etching process wasn't perfect, meaning the light waves couldn't bounce as cleanly through the material. In the end, the fastest solves were made by light that had about a 10% chance of losing its quantumness. The team speculated that when there was no added noise and the light was fully free to be in multiple paths at the same time, the light might wind up getting stuck in certain places. By adding a small amount of quantum-destroying noise, it might serve as a sort of kick to push the light down a certain path so it could continue its journey to the exit. Once again, this wasn't all just fun and games. The researchers speculated that this could explain how photosynthesis works so efficiently, since that also involves light bouncing down a complicated network of cellular stuff. So the next time you find yourself needing to solve a maze, just remember that you have a lot more options than your standard tricks, like put your hand on the wall and don't let go until you're out, or use this ball of string from a princess who fell in love with you. Okay, now somebody needs to do a retelling where Ariadne gives Theseus a pet slime mold. I would read the heck out of that.